Let's do this. The reason I'm not putting any numbers to this, like I'm not gonna say one is m and one is 2m. Let's look at the bigger picture, the bigger problem. So I'm gonna make this m1 and this m2. At the end, if you wanna make one m and one 2m and then answer all those questions, I think you'll be able to see that just fine. In fact, we're gonna answer that question first. The first problem has no friction and we're looking for a balance. So that tells me right away that the net force is equal to 0. We're trying to keep the system in equilibrium. We're gonna come back to this when we add friction in just a minute, but let's just do it this way, where there's no friction. So it's all slippery and stuff. I don't wanna spend an exorbitant amount of time on parts of this problem that I don't think are necessary. There's M1G this way and tension this way. Because the net force is 0, choosing a direction for positive doesn't mean as much because I don't have to line up the accelerations or the forces. But it's a good practice to get into, and I don't want to neglect it. So I'm going to choose a direction for positive. Now, there's no friction, but that doesn't change the fact that this is a inclined plane problem. And there are, in this case, 3 forces on my inclined plane. But more importantly, I'm not going to spend all the time anymore figuring out all the different, components. If I know it's a standard problem, then I'm going to immediately jump to the standard components. And I say it's standard problem, you have to know. If you don't know the difference between when the problem is standard and when it's not, then you will be easily tricked. But in this problem, since the net force is 0, I can choose to do the x and y axis aligned with the ramp with no problems and no worries, and therefore I know those have to be my components. But you have to start to come to grips with it. I told you an example where this doesn't work. The banked turn problem, you can't do this. We did that problem in class a bit, but understand, I wouldn't break this up into these components then. On the banked turn, I need my acceleration to be directed this way, and therefore lining up my axis with the incline doesn't work. Now, I know this, and I'm even saying it out loud, but I'm watching a number of people who are even contemplating that, and it always makes it laughable to me, because then we actually have those test questions, and you feel all blown out of the water, and if it can be aligned with the incline, then you can do it this way. And you don't have to think too much about the components. And trust me, you don't have enough time to really sit there and tinker with what you're going to do with components. You've got to know before you start the problem exactly where that problem is going to go. Now, I totally just threw away something I said a minute ago and did it a different way anyways, and we'll see if anybody can pick up on it. Everybody pick up on it yet? I didn't follow the direction I set. You should be picking up on it. Do you notice? I said this way should be positive, and I clearly made the direction of the tension positive here correct, but not here. Will it make a difference in this problem? No, it won't, because the net force is 0. Will it make a difference in other problems? Yes. But you guys do this all the time and don't think you've made a mistake. But you have. It seems subtle now, but I should have not done this. I should have done this. To be consistent. It won't make a difference in this question, which is why you'll be worried. Well, why does it make a difference later? It's because of the acceleration. You need to make sure that is the same for both problems. This doesn't have an acceleration. It has a 0. So the acceleration didn't matter. We're quite literally done with this problem. We're trying to find the condition for the angle. So that means eliminating the tension. That's what we really need to do, because tension can't be a part of our problem. We're trying to eliminate it. So look here and look here. I have 2 things that equal the tension. I want the system to balance. So I want to eliminate the tension between these two to provide the balance, which will give me m2g sine theta has to be equal to m1g. I could have added this to this and shown that the tension cancels out. I'm doing it this way because this is the way you would have done it probably had you done this problem a month ago when we first started forces. You're interested in the angle that brings the system to equilibrium. So let's go one more step. The G cancels out. That does make sense. And that gives us our answer here. The sine theta has to be equal to the ratio of m1 over m2. Now this tells you a lot. First, it tells you yes. Don't be sorry.
In the problem, though, we got that, but M1 would be 2M, and M2 would just be M.
I know.
So sine theta equals 2 doesn't exist.
Exactly. That's exactly what I want you to see. That's why that's the exact question I was about to talk about. If you look at this is only valid when M1 is less than M2, which means there is no time in which the system will balance if M1 is greater than M2. There's no angle that will satisfy it. That's exactly what this tells you, and why I purposely left those off, to give us the full range. If this happens, there's no such angle in which it will balance. Do you understand what I'm saying? So that's important to understand, and that's the kind of thing you can get from these problems. They provide a nice threshold. Now, if I look at this question, I think that that's clear. If you put the heavier weight here, the ramp is taking a component of that weight and acting on it. But if I put the heavier weight here, and I put a lighter weight on the other side, there's no way it can come into balance. Just none. But at least the math tells us that has to be true. That's why I like that question. Does that help? Yep. Now, let's ramp this problem up. I have a real problem, one that I think is an appropriate level for this class. This one is kind of just getting us started. This will handle all the people who are novices and are grasping at it. Let's do the real problem. And when I say real problem, I'm going to get rid of all of this stuff real quick. Bye, all of you stuff. Bye. Because here's what I want to do. I want you to think of something more tangible, something more fun, something that might actually require that you have to squeeze the gray matter a little bit. What if there's a coefficient of static friction of mu s between block 2 and the ramp? What size block, what size M1 will keep the system from accelerating? So I'll say that all over again because you really need to think on it for a minute. There's a coefficient of static friction between block 2 and the ramp. So what size block for M1 will keep the system at rest? Now, I want you to think about this problem for a minute. We're looking for a threshold. Now, let me get your attention again. Do you think there's a block that is too big to hang off the edge? Like if I put a block that's too big, it'll break friction? Do some of you think that there might be a block that is too small? There are two answers to this question. There's the threshold where the block is too big and causes the system to accelerate up the ramp. And there's the possibility that the block is too small and the block breaks friction going down the ramp. You have to do this problem twice. Now, pick one, and let's do that one. Do you want to talk about this one being too big or too small? We're going to do too big. So we're going to assume we're getting towards the threshold where the mass is too big. This is still a static friction problem. Net force equals 0. Net force equals 0. It's a static friction problem, so net force equals 0. It has to be. So now, let's deal with the problem. First, very little of this problem has changed from the last example. You should be able to blow through setting this problem up. So I'm going to assume you can, and I'm going to go at it with reckless abandon now. There are two forces acting in this side, M1G, and tension. And tension is going to equal M1G. Now my free body diagram for the block on the ramp is going to have a little bit more careful consideration. So I'm going to start with weight, normal force, tension, and in this case, static friction that I am pointing down the ramp. If I think the block is too big and is trying to draw the mass on the ramp up the ramp, then friction has to oppose the direction that the block is trying to go. This is a conscious decision to make the friction down the ramp, because we said we thought the block that was hanging was too big. So friction is trying to prevent it from sliding up the ramp. Now, net force still equals 0. So this will be tension minus m2g sine theta minus static friction, and that equals 0. Shouldn't be a surprise. Any question about that? And then I'm going to go with normal minus m2g cosine theta equals 0. We good so far? All right. Now, this is still a static friction problem, and it's still a problem where the net force equals 0. But if I want to figure out how big this can be, I didn't say this at the beginning, but I'm probably only allowed to have M1, M2, G, and probably mu in my answer. Maybe the angle. That's probably it. So when I'm looking at how to do this problem, I'm trying to find out where in the problem is the threshold. What's the thing that's controlling that threshold? Now, you should know by now, because we've talked about thresholds. It tends to be either forces that are able to change, or it's something that has an inequality in it. And we have a clear place for that. We have an inequality in this problem. So we should be attempting to put everything into the inequality. That should be our goal, because that's going to give us our threshold. Whenever it's a static friction problem, preserve that inequality. Now, I see a clear pathway to do that, but you might not. There's a lot here. But I do see I have an expression for the normal force. That's a good start. And I have something here I could probably use to figure out the frictional force. But I need to get rid of this pesky tension. But I think I have a place to get that from. Now, I'm not saying that, that you can do all that as fast as I can. I've done this problem, an hour ago. But you understand that those are the kinds of things you have to look for. Newton gets us to here. That's all Newton's laws can do, is get us to here. What you do with it from here has to rely a little bit on your own ingenuity and creativity. So what I see is our capacity to deal with this problem probably means I should substitute in for the tension, because I have an expression for the tension. And I should solve for that static frictional force. So let's do both of those things right now. I'm going to get rid of that T. Get rid of that. I can do this because, I have the old eraser. You guys should probably, write another line. But that's what I get. I substitute in for T and put M1G there. And I move the static friction to the other side of the equal sign. Can you do that? I hope so. And then I can dump all of this stuff into the static friction. So I'm going to rewrite all that now. And I'm going to get, on the side with static friction, M1G minus M2G sine theta has to be less than or equal to mu s M2G cosine theta. All right, that's a lot. That's everything. Now, I need to remind myself, what am I solving for? If you remember, we're solving for M1. How big can M1 be before the system starts to accelerate? So I want to solve this for M1. Do you notice that every term has G in it? So I can cancel G out, as long as it's non-zero. And I'll get M1 must be less than or equal to M2 sine theta plus mu s M2 cosine theta. Now, I like this because first, I got the right inequality. It tells me that there is a maximum value for M1. If it has to stay less than or equal to this. If it is greater than this, then the system won't stay still. That's what this inequality is telling me, that I need to keep that mass that's there less than this. And I kind of like the fact that I get the weight of the box down the ramp and the frictional force. Right? Both of those show up there. That makes good sense to me, that those are things trying to pull the box down the ramp. This box is trying to pull things up the ramp. So I like this balance. But we're not done. Right? We found one threshold. There is another threshold. So now you have to do this part. I think for most of you, you probably recognize that not much is changing here. But some of you might have trouble with what has to happen next. If we make the box too small, if we make the box that's hanging too small, what direction will this box likely go? Down the ramp. What changes if that happens? The direction of friction will change if that happens. That's what you have to do. This points this way. I don't want to redo the problem. I don't have to. Oh, you might have to. But I'm just going to go right over, say, here. And recognize that that is suddenly negative. To do this right, though, I want to be kind of explicit. I'm going to rewrite my net force equation. I'm not changing anything except for the one force. So I do the least amount of rework. So anything in yellow is going to be new. Tension plus friction minus mg m2g sine theta equals 0. That's different because this is now positive. Going to keep going. None of the next couple steps have any difference. I just have to solve this for friction and plug it in again. Everything else is going to stay the same. So I'm going to do that over here some. So static friction equals m2g sine theta minus tension. That's going to be m2g sine theta minus m1g. That's my static friction. I still have to do the whole subbing it in for my inequality. So let's do that next. I'll have m2g sine theta minus m1g has to be less than or equal to mu s m2g cosine theta. Now I'm going really fast here because this all looks familiar to me. You guys might be going a little slower. So how about I spend just 1 second sipping coffee while you guys make sure you're following the steps here. So I was slow and deliberate when we started, and now I'm picking up the pace a bit. But I know I have one more example, and there's only 12 minutes. And I know if I don't get out of the way, there'll be a whole bunch of student-sized holes as you run through that door to get out of here. So you just have to solve this for M1. I'm going to cancel out all the G's, and I'm actually going to move M1 to this side. Because it's negative, so I'm going to add it to both sides to make it positive. That okay with you guys? And I'm going to move this to the other side and make it negative. I don't have to do it this way, I just am. And I have a reason. So I'll get M1G is greater than or equal to M2G sine theta minus mu s M2G cosine theta. And get rid of all the G's still, right? Get rid of all the g's, and I have m2g sine theta minus mu s m2. Oh, wait, I said I was getting rid of all the g's. Guess we'll try that again. m2 sine theta minus mu cosine, oh, God, Mr. Shelton, m2 cosine theta less than or equal to m1, which is less than or equal to m2 sine theta plus mu s m2 cosine theta. By moving the m to the other side, I was able to join both equations together to tell me where m1 has to be. And clearly, it has to be between these two values. It has to be greater than this force, or else the box slides down the ramp. And it has to be less than this force, or else the box slides up the ramp. Oh, boy, I like this question. I like it a lot. It's got all the kinds of things in it that I think are a solid problem. Mostly, it's incredibly thoughtful. You had to realize from the very beginning that there was two possibilities of the answer. And I think that's what makes this a great question, a little bit of ingenuity. Now, once you've seen this problem, the idea here is that you've seen it. You understand now there is the possibility of two answers for some of these kinds of questions, and you need to understand the threshold in which that occurs. In this case, that threshold occurs here where there is static friction and the possibility that the box could either go up or down the ramp. That's what makes this a possible problem. It wouldn't be true if there was no angle, right? Notice right away that in this problem, if theta equals, 0, then suddenly this is a one-way problem, isn't it? If you look closely at it, what happens at theta equals 0, you'll see it. In fact, in a minute, we're going to talk about the acceleration of the system, because I think we should see that problem too. What happens if you break static friction? Now, I don't think I should have to do that problem, but I think you guys should. So I want you to consider that would probably be part B. This was part A. I give the box on the ramp a big enough tap to set it into motion. Can you come up with an expression for the acceleration of the block due to kinetic friction? Now, there is something to consider with that. So let me get all this out of the way, because once we start this new problem, everything here is changing. This is an actual new problem. Can't reuse as much of the stuff that's there. Some of it, sure, but not all of it. So I'm going to give this problem a tap, and the system's going to be set into motion. Does it make a difference if I give the problem a tap and set it into motion going up the ramp versus down the ramp? It does. If I give it a tap and set it into motion going up the ramp, friction will be down the ramp. If I give it a tap so that it started up going down the ramp, then friction is up the ramp. So you choose for me. Are we tapping the box so it's going up the ramp? Or are we tapping the box so it's going down the ramp? Okay, so we're setting the initial velocity to be this way. This sets the direction of friction. Now, let me just be honest with you guys. This is an important detail, and one that is not obvious, and you don't see it too often in even the physics books. Friction opposes the direction of motion. So in an ambiguous question, you may have to sometimes establish a direction of motion that's not given. This is one of those. On the AP exam, the modern AP exam, they will be deliberate. They will tell you what direction the box was set into motion. They don't want to have you have to make that decision. But you should be aware of the possibility. Does everybody understand why I'm saying that? I want you to be flexible in case the AP exam or in case life gives you a problem. Consider both possibilities when facing it. All right, I don't think there's anything I should do. I think you could give me the answer. I will put the answer on the board here in you get 2 minutes, because you are reusing almost everything from before, except net force equals MA. Is there anything here I need to explain? Does this look like what you would expect? So good. So we had M1G minus T equals M1A here. And you had T minus M2G sine theta equals M2A here. And normal equals M2G cosine theta. And you had to use that. These were all the steps. I threw them together fast, but this is what you had to do. And you would have done this substitution. Oh, I forgot friction. Mr. Shelton, I guess you don't know what you're doing. Minus friction equals M2A. That substitution. And then you would have take all of this over here and dealt with this putty, put them together, add them together, tensions cancel, blah, blah, blah. I never got a chance to talk about this problem. It's not even in homework, so it won't be on your test. I'm going to propose these two questions. I'm going to put them on your homework as separate for next week. You have 4 days to think about it. But I want you to think about what would happen. Is it possible I can pull so hard on the bottom block that the top block would slip off? So can you imagine a problem where I ask you what's the hardest you can pull on the bottom block without the top block slipping off? I can imagine that question. It's a good one. I like this one a lot. And I'm just sorry that we didn't get far enough to talk about it, because you can also change the problem and move that force to the top. How hard can I pull on the top block so that the bottom block continues to go along with it? It's a good question. Although it won't be on your next test, it will be on the one after it. We didn't get to cover this problem. I'll cover it next week. But, you have 4 days. You should think about it. And moreover, I would make this one M1 and this one M2, because I'm making this homework. I have 3 questions just like it. I'm going to give you 2.